Team Swift from the Ghulam Ishaq Institute.
I am Mohammed Musa Hayat, captain of Team Swift from the GIK Institute. It is my duty and responsibility to lead and represent our team in the competition. I'll be the means of communication between the team and the judges. I have great confidence in my team and I'm optimistic about our team's success this year. Let's aim for victory and soar to great new heights.
I am Huzaifa Ansari, the team manager and also the safety pilot. I oversee the team activities and keep everyone on their toes. I have cultivated a strong team for the SUAS 2023 and we have our eyes on the prize. Bring it on.
I'm Manu Ratif and I hold the position of Director of Documentation and Ground Operator. Additionally, I'm part of the competition team and I make sure that all of the necessary paperwork meets the required standards of the competition. My goal is to provide my team with a solid foundation to build upon, and I'm looking forward to document the winning moments of SUAS 2023.
My name is Ali Asad Jafri, the Director of Automation and the Ground Station Operator, and I'm a part of the competition team. I've not only worked on the autonomous systems for Recluse, but I've passed the knowledge to the budding minds of the team. We are in pursuit of excellence and look forward to exhibiting brilliance in the competition with the systems that we have developed.
I am Uzair Ahmed and I am a part of the competition team for the SUAS and the backup safety pilot. We manifest exemplary performance of Reckless in the competition.
I am Aslan Kaman and I am a part of the competition team for the SUAS. We put to use cutting-edge technology, deployed robust algorithms, optimized them to the point of near perfection, and made sure Recluse is SUAS ready.
My name is Alishba Hamsan and I am a part of the competition team for the SUAS 2023. We took up a huge challenge, worked to the bone and achieved the unthinkable. We are extremely proud of Recluse.
Introducing Recluse, a fully autonomous drone built for SUAS 2023. Equipped with advanced navigation system and a high-resolution camera, it is designed to complete complex missions in challenging conditions. It represents cutting-edge unmanned aerial technology, and we are proud to present it. The main airframe is made from carbon fiber, which makes it both lightweight and robust. The height is 2.25 feet and a wheelbase of 4.23 feet. It has an empty weight of 16.5 pounds and can bear up to 14 pounds of payload. The Hobbywing X6 motor has a maximum thrust of 12 kg per axis. Its high-strength aluminium alloy material optimizes structural design. The 23 by 88-inch propellers are used on the Recluse to provide lift and stability. Recluse uses two LiPo-6S batteries in series with a total capacity of 22 Ah. Recluse is equipped with the Pixar Cube Orange autopilot system and uses Skydroid H12 radio system and GoPro Hero 5. Recluse is equipped with 6 high-performance Hobbywing X6 180 kV motors with 23-inch carbon fiber propellers attached with 60 amp ESCs, giving it higher efficiency and more stable performance. The propulsion system can carry a load of 39.6 to 86 pounds. The propellers have an optimized aerodynamic. The objective of the SUAS competition is to design and operate an autonomous unmanned aerial system that can complete a mission within a specific time frame and meet certain requirements. These requirements include keeping setup time under 15 minutes, mission time under 30 minutes, ensuring 95% or a higher waypoint accuracy, and delivering an object within 15 feet of a potential drop location without damage. The system also needs to be able to detect objects autonomously and classify them as standard or emergent, communicate between the drone and ground station through encrypted communication, and use video transmission. To achieve these two goals, the system requires two operators, a safety pilot and a GCS operator. Obstacle avoidance is achieved through the use of sensors, algorithms, and classifiers. The system must be optimized for operational excellence and able to adapt to changing conditions during the mission. The design of the UAS plays a crucial role in ensuring that the system meets all requirements and can perform the necessary task efficiently and accurately. We chose a hexacopter as our aircraft system because of a high payload capacity, high maneuverability, and compact design. Recluse is made wholly of carbon fiber, making it lightweight with greater tensile strength. It has a wheelbase of 4.2 feet and a height of 2.25 feet. Recluse has a full load weight of 36.2 pounds and can fly for 45 minutes at a maximum speed of 28 miles per hour without any complication, making it possible to complete missions in a minimum time of 25.7 minutes. choice for the camera: weight, cost, effective megapixels, and hardware compatibility. Recluse uses the GoPro Hero 5 camera and relays the photos to the ground station for classification and review. It takes a picture depending on the algorithm ability to recognize when and where it is prompted to take a photo for image classification. This 12 megapixel camera can resolve objects required by the competition with high accuracy due to its high horizontal FOV of 122 degrees and vertical FOV of 94 degrees. The camera offers a maximum resolution of 4K with maximum 30 frames per second. We will be using a 2-axis brushless gimbal for camera stabilization and 2-axis control. The team uses an algorithm to autonomously detect, localize, and classify the objects from an image. A convolution neural network (CNN) was developed to autonomously detect, localize, and classify objects. A custom modified deep learning architecture called YOLO is used to detect the underlying shapes and the class of emergent objects. The architecture was trained on a customized data set that contained about almost 700,000 target images. The data set included all possible combination of target characteristics such as varying heights, terrains, obliqueness, rotations, and noises. Our drone can safely drop 500 grams bottles from 75 feet using parachutes, making it the perfect solution for emergency supplies, food and water drops, and more. Our payload consists of 5 bottles, each weighing approximately 500 grams and holding 16.9 ounces of liquid. They're supported by a sturdy carbon fiber frame with flaps that hold the bottles in place while in the air. Each bottle is wrapped with a durable shock-absorbing material and attached to a folded parachute, ready to be deployed when it's time to drop. To determine the optimal drop time, we use our drone's advanced autopilot system, which calculates factors such as wind speed, direction, payload weight, and parachute size. The drone hovers at a height of 75 feet when the target location is detected, and the autopilot system activates a corresponding servo, which rotates the flap beneath the compartment holding the bottle by 90 degrees, releasing the bottle within. As soon as the bottle is dropped, the parachute opens, allowing for a controlled and safe descent to the ground. SkyDroid H12 radio system operates in the 2.4 GHz frequency range with a maximum range of 30 km. To establish communication between the drone and the ground station, the SkyDroid H12 radio module is connected to the Pixoc flight controller. 900 MHz telemetry allows the wireless communication of data from the ground station to the drone. It can operate in the range of 900 to 928 MHz frequency. The expected performance of the SkyDroid H12 radio system is reliable communication with low latency and high throughput within the specified range. Recluse is powered by two high-capacity 6S batteries with a total capacity of 22,000 mAh, providing increased power output for advanced flight performance and protected by an impact-resistant waterproof casing. It provides Recluse a longer flight time without compromising on the functionality of other systems powered by it. Recluse is equipped with 6 high-performance Hobbywing X6 180 kV motors with 23-inch carbon fiber propellers attached with 60 amp ESCs, giving it higher efficiency and more stable performance. The propulsion system can carry a load of 39.6 to 86 pounds. The propellers have an optimized aerodynamic shape, which gives the aircraft system its high thrust. The Recluse was able to reach an altitude of 656.2 feet during the flights. It was able to reach a maximum speed of 30 miles per hour. To accomplish the task of obstacle avoidance, our team utilized multiple single-direction TF Mini S micro lidars. An algorithm created by our team utilized waypoint coordinates, obstacle zone centers, and obstacle zone radii as inputs. The algorithm's initial task is to find the shortest path between the waypoints without changing their order. To accomplish this, the algorithm employs the practical and effective Dijkstra's shortest path algorithm. In cases where there are obstacle zones present between the waypoints, the algorithm selects an alternative route that is both safe and efficient. Subsequently, the sensors installed on each side of the hexacopter detects any approaching UAVs and modifies the flight path to avoid them while maintaining the shortest possible route. Throughout the design process, our team explored several alternative options before settling on our final design. Initially, we considered quadcopters as an alternative to the hexacopter, but they had limited payload capacity and couldn't lift as much weight as the hexacopter. Jetson Nano was selected among the two other leading computer companions as it had a high processing speed and more RAM, plus it was a cost-effective investment. Even though the Q-Pilot Orange Plus was the expensive choice, we went for the highest processor speed and user-friendliness among the choices at hand. We also tested various frame materials and designs, including pentagonal frames, rectangular frames with different orientation, and materials such as steel, wood, and aluminium. However, after rigorous testing and analysis on SolidWorks and ANSYS, we concluded that carbon fiber was the optimal material for our drone's frame. We went with the Hobbywing X6 as it was giving us great balance between thrust and cost. The downside was weight, however there were no negative implications to it. Taking in view the cost, capacity and weight of the battery to provide sufficient flight time, we went with two 6S batteries coupled in series. The safety risk and our actions to mitigate them are summarized in the following tables. Rigorous trainings and courses as well as guidance from our advisor helped us navigate this aspect of the competition. Testing over 2,500 images, we had a test accuracy of 96% with our 12 megapixel GoPro Hero 5. We were able to come up with a test set of 200 different alphanumeric colors and shapes, out of which 79% were auto-detected and 70.5% were auto-classified. The airdrop subsystem underwent rigorous testing to ensure its performance. In total, 50 drop tests were conducted both autonomously and manually, out of which 49 were successful with an error of 4 feet. The SkyRoad H12 radio module communicates telemetry with the ground station using a 2.4 GHz frequency. It had a range of 4.4 miles in air and 0.93 miles on the ground. The subsystem was able to handle interference from other devices such as Wi-Fi or Bluetooth without any significant impact on telemetry data transmission. To test its capabilities, 143 flights were carried out under different conditions with an accumulative flight time of 23.8 hours. The Recluse was able to reach an altitude of 656.2 feet during the flights. It was able to reach a maximum speed of 30 miles per hour and stay for an average of 45 minutes in the air. The stability and maneuverability were smooth and efficient. The aircraft was tested in windy condition of up to 28.8 miles per hour on the sea view in Karachi. The autopilot's advanced flight capabilities include waypoint navigation, automated takeoff and landing, and automatic mission planning. The Cube allows us to fly safely with precision and control. We were able to attempt 67 autonomous flights with a 100% success rate. With an error of 2.3 inches, we were able to navigate through all of the waypoints we set for ourselves. 300 obstacles were encountered by the Recluse, out of which it was able to avoid 298 of them, giving us an accuracy of 99.33%. Our team completed the pre-flight checks within 10 minutes. Once our system was operational, we had a briefing of 5 minutes before executing the mission command. During the mission, our aircraft flew along a waypoint path and autonomously came within 10 feet of each waypoint while avoiding static and dynamic obstacles. To ensure connectivity between the ground station and aircraft, we used a radio antenna. The aircraft detected a standard and emergent objects on the ground, classified and localized autonomously on board, sent the signals to the ground station where its performance was monitored. The aircraft was able to drop the payloads within the target's radius. After all the payloads were dispatched, the UAS activates the return to launch mode to find its way back to the starting location while avoiding any hazards. After the UAS touched down, the crew carried out post-flight inspections to guarantee safety before clearing the scene. We conducted at least 15 mission tests and solved the arising problems by checking the checklist over and over again to ensure normal and emergency procedures were in place. With each mission test, our scores improved as we continued to troubleshoot. Our team achieved a high score of 95.25%, which was broken down into 84% for timeline, 100% for operators, 97% for airdrop, and 100% for operational excellence judged by our advisor. We expect to achieve better results during the mission demonstration.
सब्र करें, चलाएं हम।
Low altitude 0. Mode change to auto. Head.
Five, 60, 55, 50, 45, 40, 37, distance is 50, altitude is 38, distance is 25, altitude is 30, distance is 20, distance is 15, altitude is 20, 10,
Arming, stand clear, taking off.
Over the course of the past year, a systems engineering approach was implemented to develop and improve the performance of the UAS, designated for package delivery. The system was refined, tested and enhanced to ensure efficient mission execution in line with the requirement of the multiple package delivery companies. Major subsystem overhauls were undertaken, including custom development of airframe parts, onboard parallel processing and deep learning-based image classification algorithms, all of which were thoroughly reviewed during testing and integration. The development process spanned 1 year, during which meticulous system testing was conducted to train team members and expand their knowledge and experience. The result is a reliable system capable of avoiding other UAS traveling to the customer, identifying potential drop location, and delivering packages to safe location.